can generate a stable walking, but then it will be difficult to know why it is working. And if you want to know more about that, yeah, we about 1.5 years ago we edited this book, and some of the people here already contributed to that, and we tried to cover different aspects, different levels of modeling into this book, and also design and control. Let me go to the main topic. The first topic is the locomotor self-function, and if you look at this windmill, you see there are 3 rings which work together, and if you look at our body, we also have 3 rings which are the stance, swing, and balance locomotor self-functions, and they also work together. In the windmill, they are fixed, but in our body they are coordinated, I would say, and we want to know how they are coordinated, and if we control one of them, and I mean separately, if we control them separately, how can we coordinate them? In this talk, I just want to say some examples of each of these locomotor self-function. The first one is the stance self-function, and we all heard a lot about the template models like sleep. You see that with the sleep model, we can explain human hopping, we can generate some gating robots, and it is a good model for a stance self-function. I don't want to explain more about that, but you know the work from Hartmut, who developed the walking and running with this sleep model and bipedal sleep model, and generate similar ground reaction force patterns, center of mass movement, and so on. It means that our template model for a stance leg control is a sleep. It could be other things, but we use this. And I talk a bit more about the balance self-function. And again, the VPP concept is there, and I just repeat that VPP says that the ground reaction forces go through a point above center of mass, and it can convert the inverted pendulum model to regular pendulum model, which with this you can say something about stability. You cannot argue that, okay, if VPP exists, then it is stable. If it is not existing, then it is unstable. But there are some relations we are working on. For example, I can give you an example. This is a master study of my students, and we compare the ground reaction forces in healthy subjects. This is for walking, and Parkinsonian gait. And in Parkinsonian gait, you see that the ground reaction forces are intersecting below center of mass, which says that it cannot be modeled by pendulum, but by inverted pendulum. It means
is this healthy VVP of people of the same age and same walking speed, etc.?
No, they are not from the same age, but why does it matter? For healthy subject, basically it is above center of mass if you look at walking, but for elderly people, you can see that there are, not elderly, sorry, for Parkinsonian gait, you can see that there is a kind of instability in the movement, and at each step you can say it is unstable, but from step to step you merge some unstable steps, and finally you generate a stable gait. This is how we yeah. You want to say something?
It could be if these patterns are likely affected by walking speed, right?
That's what my question was. Yeah.
No. For walking speed, if you go for the same walking speed, still in healthy people, you see VPP above center of mass. The distance will change, but it will go higher. Okay, and then we developed this biomechanical template model based on VPP concept, which is force modulated compliant. We consider a spring here and use the ground reaction force to tune the thickness of this spring. With that, we can precisely predict hip torque in humans in VPP. And if we look at human data, you can see that it's very surprising that if you divide hip torque by leg force, you can see kind of linear relationship at different speeds. These are different speeds that you can see. For example, here is 0.5 meter per second, which is the same speed or even lower than the speed that we did with the Parkinsonian patients. This shows that, okay, it is linear. Then here, if you divide tau by f, you can also have the linear relation. It shows that the VPP concept is working with based on human experimental data. And now we took another step and replaced the springs with human muscle model. And if first you ignore the red part, if you look at the black part, you see something like reflex model in Hartmut's reflex model, and in that model, the reflex from the same muscle is used as a feedback signal. Here we use the ground action force to tune the activation of the muscle, and with that we call it neuromuscular FMCH or NMF model. And then we see that it can generate some stable gait, and we add another layer to tune this gain. You can see here it could come from upper level, for example, from brain to tune the control gain. And with these different levels of complexity, we found that with the FMCH model, we have this pattern of attraction. With NMF, just by considering the intrinsic behavior of the muscles, you can somehow double the pattern of attraction, and definitely with the adaptive version, you can increase it more. If you want to know more about that, we can discuss about that later. Yeah, this is the paper which is published this year. I want to talk shortly about the swing or template model, about simulate self-function. And our model is very simple. We just have a double pendulum with wired springs, and during swing phase, we don't change anything. We preset the rest length of this spring, and with that, we could mimic the muscle force behavior, and also here you can see the kinematic behavior. These angles, alpha, phi, K, which is the knee angle and hip angle. You can see it in the right side, the human data, and in the left side, the model prediction. So from here, I switch to the second topic, which is the sensor motor map. If I talk about template model, which is basically a mechanical template model, we can also use them as control template models. And it could be a mechanical template model, but this model, which is developed again by Hartmut in 2003, is a reflex control for hopping. You have the muscle, and you have the reflex control using this, the signal from the same muscle to tune to activation. You tune the activation. And recently, one of our students worked on how we can blend different reflex signals and develop different metrics. I mean, we have the length feedback, velocity feedback, and force feedback of the muscle. And here in this triangle, you can see that, for example, if you are here, then the velocity feedback gain will be 1, the other will be 0. If you are here, all of them are equal. And if you go to the corner, at each point you have a specific combination of these gains, the summation will be 1. And with that, we search for first the best feedback to have the highest performance. Performance here means highest hopping height, and in this corner you can see, here you can see the stable region, and the highest performance is gained by a point close to pure force feedback, and which means that with force feedback you can have the higher hopping height. And if you look at the same thing, but looking at the efficiency, the optimal solution will be here, close to length feedback. And if I want to summarize this, I could say that force feedback gives you a handle to performance, length feedback to efficiency, and if you go for velocity feedback here, it is unstable, meaning that it stops after several hops, it stops. It could inhibit hopping. And yeah, we can say that it's a kind of modeling of the pedals that you have in cars in Europe, at least. I'm not sure in US maybe you have pedals, but yeah, length feedback will be clutch, with which you can address the efficiency. The velocity feedback is working like brake, because you can stop the movement, and with the force feedback, you can it works like a gas pedal in car. You can increase the performance. Yeah.
Efficiency just finalized by initial, right?
The energy which is consumed in the muscle. It's not a conservative model. No, for all of them. Okay. Yeah. If you look at the other properties, stiffness and other things, you can see similar behavior. Just here you can see some small stable solution in the with force velocity feedback, and we implemented that on the robot, and it works perfectly with the force feedback. It can hop stably in one gear. And yeah, with this I want to wrap up. And yeah, from the locomotor sub-function, I can say that we introduce a kind of modular organization for motor control, and we can also develop a kind of network to move toward the neuromuscular models or the anchor model, and the task-specific exploration of sensory network can be studied with sensory motor maps. And we also started to implement these for assistive systems that I don't show in your time. So thank you.
What does the gain, summation of the gain, a gain being one, what does that have any?
Why or?
Why one?
Yeah, because we just want I go to here. You see this is our network basically. We blend different reflex signals, and in total we want to have a meaningful evaluation of which one is important. And if one of them is 1, the others are 0, it means that you just use one value, and to make them comparable, we think that within this triangle you can define with the distance to different points, you can define how important this reflex is. And within this, you can see that the summation will be 1. We have also other gains like GL, GB, and GF, which are for normalization.
Your VPP data looks really, really nice. Ours doesn't look so nice. Are you cutting left and right?
Sorry, I couldn't hear what VPP looks nice and what?
Yes, it looks perfectly going up there. Like you have lots of vectors, especially at heel impact, and so going over. Are you cutting these 5% on both sides?
Not really. This is about where you draw the ground reaction forces in the single support or double support. Here is the single support, and also
You're taking out the double support.
yes. And the second point is that the coordinate frame is centered at center of mass, and also the y-axis is oriented with the trunk orientation.
Yeah,
It's something that
the
people.
last ones are normal, but I didn't realize that you're only showing actually the single stride. And this is walking. Which speed is this for the Parkinsonian, and which speed is this for the healthy? Because that's the VPP point in your case seems to be at top of the head, right? It's 1.8 meters. And in the Parkinsonian, you're dropping by 0.3 meters. Is this correct?
1.8.
Like from the ground?
Here, from the ground, you mean?
Yeah. Is this correct?
From ground, yeah, it depends on where this. Yeah, it could be. Yeah, it's basically about. It could be from 20 to 80 centimeter above center of mass. This is what we observe at different speeds and different.
Okay. And which speed is the Parkinsonian?
If I remember correctly, it's 4.6 meters per second.